Hello and welcome to my presentation today on knots and links in spatial graphs. This article interests me because I took knot theory over the summer, and I felt like these two topics were related close enough that they validated some sort of article that really connected the two and talked about the two together. The main focus of this article are the graphs K6 and K7 and looking at those as what we call knots. Let's go ahead and get into it. Definitions wise, I have first a knot, which is an embedding of a circle in 3 space. The circle part just means that as we travel around this black edge, it never jumps from one place to another. It's a continuous loop. So that's why we call it a circle. It's not technically a circle in geometry terms, but there you go. And the 3 space idea is just that we can see where this circle, this knotted piece of string, goes over and under itself to form a knot. Because if we had something that didn't go over or under itself at all, we would just be left with a circle in the normal definition of it, and that would be considered an unknot or a trivial knot. For some of the other knots that I learned about, and they will come up later in what we talk about, the first one is a polygonal knot, is a knot whose image in 3 space is made up of straight line segments. This is an image of that knot that we just saw on the previous page. That trefoil knot is the name of it, and this is what it looks like as a polygonal knot. And then a tame knot is a little bit looser of a definition than a polygonal knot in that it's just has to be equivalent or isomorphic to a polygonal knot. That's what a tame knot is. A spatial embedding is where we use that idea of a tame knot. It's a representation of a graph that's embedded in 3 space and it is tame. So not only do we have the restriction that it has to satisfy the idea of what a knot is, but also it has to have some sort of equivalence to a polygonal knot. This is a spatial embedding of K6 that we're going to be using in just a little bit. A link is a collection of knots that do not intersect but may be intertwined, and we'll talk about that intertwining idea here with linking number. Linking number is a knot invariant that determines the number of times that a component of a link passes through another component. So the thing with linking number is that we're going to be looking a little bit on how to determine linking number, and it requires that we set an orientation on the knot or on the link itself, and again an orientation on each component. So I'm going to have both of these going in sort of opposing directions, but just to show that when I look at at a crossing between two components of a link, I'm looking at the easiest way I can describe it is I'm looking at the slope of the overstrand. This strand is going over, and it's a positive. I would think of that as a positive slope in Algebra 1 terms. So we get a +1 for that crossing, and this crossing the same thing. As this component is going this way, it is the overcrossing, and it also gets a +1 assignment for that crossing. To calculate linking number, you're going to take the sum of all your intercomponent crossings and divide by 2. So in this case, I get 1 plus 1 is 2, divided by 2 is 1. That linking number of this is 1, meaning that these 2 components are held together 1 time. They're intertwined 1 time. This, by definition, is called the Hopf Link, and it is typically seen as just this, a linking of 2 circles. This one over here, if we do that same orientation and we look at the crossing values on this one, the overstrand is going up and left, that would be a -1, and here it's going to the up and right, that would be a +1. When I take their sum, I get 0, divided by 2 is 0, so my linking number is 0. What that really means is that this would be a trivial link. And that just means that these two links could be pulled apart and separated. We'll be looking for those later as well. The first theorem that we're going to talk about today is that every spatial embedding of the complete graph on 6 vertices that we know as K6 contains a non-trivial link. So we're looking for a link, as we saw on the previous page, that doesn't have a linking number of 0. Okay? So for the proof of this, we're going to let G be a spatial embedding of K6. And we're going to define lambda in Z sub 2 such that lambda is equal to the sum of the linking number of C1 and C2, where C1 and C2 are disjoint cycles of K6. Obviously, with K6, in order for us to have a cycle, we need 3 vertices minimum to make a cycle. And with 6 vertices total, that means that we can only have 2 cycles of K6. So that's why we just take the linking number of C1 and C2. Now in that, there are 10 pairs of disjoint cycles of K6. As there are 6 choose 3 ways to pick 2 triangles out of 6 vertices, that would actually give you, what did I say? That would give you 20 ways to pick 2 triangles. But since when we pick the first triangle, we automatically pick the second triangle, something like choosing 1, 2, 3 for one of my cycles is the same as choosing 4, 5, and 6. Because choosing 1, 2, and 3 automatically chooses 4, 5, and 6 for the other one, and vice versa. So there are 10 disjoint cycles of K6. And we're going to observe how lambda changes under different crossing changes. Because we want to talk about all spatial, sorry, not all, but every spatial embedding of K6, we're going to assume that we can obtain new embeddings of K6 through changing crossings, sometimes one at a time and sometimes more than that. If we have a crossing in a single component, let's say that we have a triangle here and it crosses itself. Let's say that it's an overcrossing right here. And we say that it crosses itself. We don't count that in linking number. Linking number is defined as being crossings between 2 separate components. So anytime we have this, we don't change the linking number. The linking number won't be affected at all. And even though in the spatial embedding of K6 that we saw a little while ago, that didn't happen. Never did I have 2 edges crossing each other. If we consider all spatial embeddings, or we consider every spatial embedding, there's a possibility that that could happen. This means that the linking number won't change, so lambda won't change. And then if we change a crossing within different components, then I get something like this. I've taken something that maybe was a -1 crossing, and I switch that crossing to go the other way to where the overstrand is going up and to the right instead of up and to the left. That's going to change that assigned value from -1 to +1. So it's going to change it by a value of 2. Now, obviously, if I would have started with a +1 crossing here, if I would have flipped this around, and I started with a +1 crossing and I turned it into a -1 crossing, that would change it by -2. I could also get a change of 0 if I changed multiple crossings and they ended up sort of canceling each other out. So changing those changes the sum by 2, 0, or -2. That's the value of the linking number. That's also meaning that the value of the sum is going to change by 2, 0, or -2, or even a factor of 2 or -2. Sorry, not a factor, but a multiple of 2 or -2, which lambda being in Z sub 2, if it's changing by any factor of 2, it's not going to be changing at all, because You know, if we think of modular arithmetic and we add something in z sub 2, we add a multiple of 2 to a value, it's not going to change its value in z sub 2. So lambda is still going to be unchanged. And what that tells us is that if we can find a pair of linked triangles in k sub 6, then we know that in every embedding of k sub 6, there's going to be a pair of linked triangles. So we're going to start with this one. We're going to start with this spatial embedding of k6. And I went through the extra effort to find all 10 of those, and it does turn out that the majority of the time we're left with trivial links. All of these are these first 7 disjoint cycles of k6 are trivial links. You can see that by the fact that no components cross the other component. Then we have 2 other disjoint cycles of k6 that end up giving us a little bit more interesting trivial links, in the sense that they're at least going over the other component, but we notice that we have an overcrossing here and an overcrossing here. If we calculated the linking number the same way we did in the definition, we would realize that we could split these 2 links. We could just pull them apart. Nothing is holding them together. Same thing with this one here. The linking number is still 0. In our last one, we have an undercrossing here, followed by an overcrossing. And if I were to calculate the linking number of this, it would actually be -1. Most of the time that we talk about linking number, we are talking about an absolute value. So it is okay to say that the linking number is 1 in this case. And we get that these 2 disjoint cycles are linked. They're 2 triangles that are held together. They're intertwined once. So if we look at lambda, lambda would be the sum of all these. And the sum of all those linking numbers is 1. So since for every spatial embedding, lambda is going to equal 1, that means that every spatial embedding is going to have a pair of linked triangles. So that is the first proof completed. For the second proof, we are looking at every spatial embedding of K7, or the complete graph on 7 vertices. In this case, we want to show that it yields a non-trivial knot. We're going to go over more of a sketch of this proof, more of a sketch than the last sketch, because the 2 proofs are pretty similar, but there are some heavier levels of knot theory that's required for it. So first, we're going to be given a spatial embedding of K7, and we're going to define sigma in Z sub 2 such that sigma is the sum of alpha of C, where alpha of C is defined as the ARF invariant of C, where this is where the higher level knot theory stuff comes into play. We get C sub plus, C sub minus, and the linking number of L1 and L2. That involves a smoothing of the spatial embedding of K7, where you're looking at all the possible crossing changes. You're looking at every crossing you have, changing the crossing from what it is to its opposite, and then also, so if we look at, we have this crossing, we're going to look at, if this is our original crossing, we're also going to look at its opposite, so just changing the crossing. We're also going to look at what's called smoothing the crossing, and coming up with different components with that, and how that affects the linking number. So again, that's the part that we're skimming over a little bit, because it does involve some higher level looking at the knot and determining what the linking number is going to be, and as well as the ARF invariant. But the ARF invariant is a really neat idea, because it uses these set of special crossing changes where they talk about it being pass equivalent, or a pass move, where you're kind of changing 5 crossings at once. But it determines whether a knot is truly knotted or is the unknot. The ARF invariant of some cycle C is 0 if the cycle is equivalent to the unknot, and it's 1 if it's equivalent to that trefoil knot that we saw in the definition of knot. And that's a huge statement, just to say that the ARF invariant is, well, first of all, it's either 0 or 1, and that if it's 0, it's the unknot, and if it's 1, it's the trefoil. That doesn't mean that every knot is going to boil down to either being the unknot or the trefoil. This is another part where we're kind of skimming through this idea of the crossing changes. Like I said, it changes a lot of crossings, and we are drastically changing the style of knot that we have when we do that. So let's go ahead and keep going. But similar to Theorem 1, in our case here, sigma is kind of taking on the role of lambda in Theorem 1, where it's in Z sub 2 and it's the sum of something. In this case, it's the sum of the ARF invariants, but the ARF invariants are also in Z sub 2. And so just like in Theorem 1, we would see that sigma is unchanged by crossing changes and by varying embeddings. So if I change a crossing, it's going to change it, the same is going to apply. It's going to change it by 2, 0, or negative 2. That's what it's going to change the linking number by, which alters the ARF invariant by 0, 2, or negative 2. And since that's in Z sub 2, that's going to change sigma by 0, 2, or negative 2, which again in modular arithmetic, modulo 2, we're going to be unchanged. So that really implies that if we can show that one embedding is knotted, then all the embeddings are knotted. So we're going to look at this embedding of K7. I have numbered the vertices so that we can use them as a reference, but we're really trying to find one knot in this embedding of K7. And in fact, for us, this is a Hamiltonian cycle that hits all 7 vertices. It goes from 1 to 6 to 3 to 2 to 5 to 4 to 7 and back to 1. Now if I get rid of all those edges that I'm not using and I simplify this a little bit, it still looks a little tricky, and I don't know that I could tell you right off the bat what it was, but in knot theory we can go over a lot of what we call Reidemeister moves, where basically I can turn I can turn this this arc right here, I can convert it to being an undercrossing behind vertex 5 there, and then continue doing that, and I can actually turn this arc that goes from 1 to 7 to 4, I can turn that straight into an undercrossing here and going to 4, with 7 being located on that strand. So that's what we have here. Just kind of tighten that piece a little bit. And this is actually a pretty common showing of the trefoil knot itself, because the trefoil knot is what we call a twist knot, and this is a 2-twist knot. But it is the trefoil knot, and we can see that the over and under crossings match up. If we start at 1, and starting at 1 here, I can go around my loop. It goes under and over, over and under, over and under, over, under, back to 1, over, under, over, over, under, over, under, over, under, back to 1. One thing that I found in my additional research, trying to figure out kind of just what the ARF invariant was, they actually showed me that every polygonal spatial embedding of K7, so anytime we have K7 that is made up of straight line segments, and this one that we have here is a tame embedding of tame spatial embedding, in that it's equivalent to a polygonal knot. We could turn all these edges into straight line segments, and we would be just fine. We wouldn't be breaking down any part of the knot at all, any part of the spatial embedding at all. But anytime you have a polygonal spatial embedding of K7, it actually contains a trefoil knot, and that's a pretty pretty big statement right there. So that being said, thank you for watching. The references I used, I had used the Not book a little bit, as well as the Not book was our textbook for knot theory, as well as the article. A lot of the information came right out of the article, but some of the additional information came out of the Not book. Thanks, and we'll see you later.